Hey, hi. So today we will be discussing system design of Yelp, Nearby, or Google Maps. For example, when you do queries like get hotel near me or get some of the bank ATMs near me. So these kind of queries are the sort of system that we want to design today. So that's the feature of the system that we want to discuss system design. So let's talk about the functionalities of the system. So the core functionality of this system is search nearby places. So basically what you give it a query, search words query, and something like search nearby electrical shops near me. So something like your query will be something like the search will be electrical shop, latitude, longitude, and 2000 meters, which is like 2 kilometers. Such 2000 places which are 2000 kilometers around this area. There will be other functionalities which are supported by this system. One obvious will be add places, where you add a place, and then when you go to Google Maps, you can also add a review, that is comments, to a place, and you can add rating to a place. So that will also do. Now, for any system design problem in an interview, first you should discuss and settle down what are the functionalities of the system, and then let's go to what will be the scale of the system. So let's assume that our system will have like 1 billion places, and it will be having like serving like 100,000 queries per second. So that's a pretty good big enough scale to design for. So now let's discuss how much space a single space will take, so that we can like calculate the data for all the spaces. So it will be like a single place will have a place ID, latitude, longitude, name and description, and where this name, description, tags, images, address are long strings. So let's assume that on an average place text one place equal to 10 KB of data. Since it is 10 KB of data, so what will be the total memory which will be consumed by the system? So it will be around 10 to power 9, that is 1 billion into 10 KB, and that will be 1 terabytes. 1 terabyte is not a lot of data. Today we can get like 1 terabyte data for like $100, 100 US dollars, you can say. So that's not a lot of data. So those hard disks are easily available. The main thing that for solving this kind of a problem is that can we solve it that answer the search queries efficiently. So for that we'll have to divide our data. So like any system design like interview or anyone, let's solve it for a single system. Once we solve this problem for a single system, then we can see how will we distribute our solution to figure out all the data. So basically let's start again with what are the queries that we have. And the queries, it's a string search, where you give in the search nearby electrical shop me, and near a given location, which is the latitude and longitude, and the radius along which is surrounding that latitude and longitude. So for this already we know that in Elasticsearch this feature is already implemented, where you add the latitude and longitude at geo point, and then you can search using the geo distance queries. So that feature is already implemented. So what we are going to do it for a single system, we are simply going to have a Elasticsearch index and keep all the data in it. So now for single system, our data should be fit into a single system. So let's assume that our system will have like 1 million places. A single machine will have 1 million places, or a single Elasticsearch index will have 1 million places. So that's like 10 GB of data per index. Now 10 GB per index is not a very large index, it's a good enough index, so it will be efficient in the terms of queries. Let's also calculate how many queries per second on an average index could face. This is a tricky thing to calculate. Why? Because basically if there an index contains data for a very crowded place or lots of places, not crowded place, for famous places, then it will have search high search traffic. But still, let's try to find out what will be the average search query per second. So for 10 to the power 9 places, there are 100,000 queries per second. So for a single system is keeping 1 by thousandth of data. So we assume that okay, a single system will also take 1 by thousandth of all the search traffic. This may be an incorrect assumption, but we'll see how we will introduce replicas, so that if a particular machine or index is getting more queries than the average, then it can satisfy that. So for now, our machine, each index will serve around 100 queries per second, which is not a lot. It's like not mild traffic, but it's doable, easily doable for a machine. Up to 1000 queries per second also, it's doable for a machine, depending on the size of the index, which is quite small in our case. Next, once we know that our Elasticsearch has already implemented these functionalities, so let's talk about how will we scale our system. We will scale our system using quadtree. So quadtree is nothing, it's basically consider whole world as a tree. So this whole world is a rectangle, and there the dots are the places in it. And what we do, so basically in each quadtree we have assumed that we will keep 1 million places. So let's suppose, for a small example, in this quadtree we assume that no rectangle should contain more than 2 dots, that is 2 places. So we divide it in 2 parts, and again we divide that upper right rectangle in 2 parts, so in 4 parts, sorry. So we'll see that there is no rectangle which is having more than 2 points. Now again, just assume that make that calculation for 1 million places. So we'll keep dividing the quadtree and until we find a leaf node which has less than 1 million places. So the leaf nodes will be actually hosted on a web server, and rest of nodes will be hosted on a service quadtree, which can be accessed through a service. So quadtree nodes quadtree can be fetched from a service, or we do not need to fetch the whole quadtree. We just need to fetch we will have a location service, and what it will give us, get leaf nodes near a location. So what we will give it, we'll give it a latitude and longitude and address, and it will return a list of leaf nodes which contain the actual Elasticsearch which contain actual places data. So so let's decide on the format of the results so that we can move ahead. So each row will be something like this. Okay, so each row will have a quadtree ID, and then it will have a Elasticsearch ID, index ID, which will be the Elasticsearch index on the machine, and it will have a list of IP addresses of the web servers which hold that Elasticsearch index. So as you can see, we have multiple IP addresses, so multiple web servers. So if this is replication, we are using this so that if a single server like IP1 goes down, then data can be fetched from IP2 and IP3 also. So it gives us that benefit. Another benefit which it gives is, let's suppose a single our queries per second for our machine increases for that particular index. Let's suppose index 1 increases, then what we can do is we can simply increase the number of web servers which hold this index, so IP4. So benefit this number of queries will be distributed across 4 machines as compared to 3 or 5 machines. So this is how the read queries will be handled as if Elasticsearch index become more hot, you can say read request come more and more towards that. So this is how we will like distribute the whole data. We will have a service, we will try to fetch all the leaf nodes, and at max it can like fetch like 9 leaf nodes, and fetch leaf nodes for each leaf node. And what it will do, it will actually not return a list of IP addresses, or it will, for each leaf node it will choose, we will choose an IP address at random and fetch nearby places, let's say 100 places. Okay, and then we merge all the results based on sort order. And now your sort order can be something like a place with the highest rating, or it can be a place with the nearest place. So these things can be done in the application layer also, it can be done in the Elasticsearch also, wherever since reviews are a changing thing, so better to, I mean both the places can be done with, we can discuss on the pros and cons of each approach. But basically this is how we will like store and distribute on the data. So basically there will be a quad tree which will hold like link to all the leaf nodes, and leaf nodes will contain the data, and will when searching we'll find a quad tree for based on the location, that is IP address, and we'll find a list of quad trees, and we'll make our request to all the leaf quad tree nodes and merge the results and return the top results. So that is how it will occur. Now what happens in case of failure? Let's suppose our machine failed, or what happens is our there can be failure due to operational overhead, due to Elasticsearch index failure, some error in Elasticsearch index. So there is one reason I have kept the Elasticsearch index as a small 10 GB only. So the idea is that if there is any error which comes in Elasticsearch index, then we do not try to remove the error manually. What we can do is we can automatically create a new index with that data, and just update it, that index to every other place. Let's suppose IP1 index 1 has error. So what we do is we simply create an index. Let's suppose machine failed, then let's suppose we create a machine like IP6, IP5, and keep all the indexes come that were in IP1. So we will take the index 1 and recreate the index in IP5, and where for all the IP1 values we will replace IP5, and our job is done. So let's calculate how much time will it take. And this can be done automated way, no manual intervention is needed. So system is like self healing system. So let's calculate how much time will be needed for failure recovery per index. Now multiple indexes can be recovered parallelly. So let's calculate for one index. On that basis we can get a rough enough idea. So basically each index has 10 GB of data is stored, and 10 to the power 6 places is there. So what we can do is we can back up all this data in the cloud file storage like S3. That is one of the simplest ways to back up data. We can back it up time to time, every 6 hours or 24 hours. And when an error occurs, then we simply, we do 2 steps. We fetch the 10 GB index data, and plus add one by one all the rows to the Elasticsearch. So what will be the time taken? Time to fetch 110 GB data. Typical speed is 100 Mbps when fetching from S3 when you are in the same data center. And then how much time will it take to add 1 million rows? So from the speed itself, you would have already calculated that it takes 100 seconds to fetch like 10 GB data, and to add like 1 million rows to an Elasticsearch, it will take like 250 seconds. So approx 6 minutes it will take. So this is our error recovery time. And now one thing that we should note is during this failure recovery time, it's not that the system will be completely down, because even if a single machine is down, we know that our single index will be on multiple system. So unless all the systems are down, which is like sort of bad luck or some very event like earthquake, high intensity earthquake has happened, it will not happen. So our system will be highly available. Whenever system fails, just pick up a new machine, replace the old indexes into the new machine by fetching from file storage, and just update all the IP address values of the failed machine with the new IP address of the new machine. So that is how we can build a machine in parallel. And so this is how it goes. So this was all about storing the doing the nearby feature in these places. Now you can ask a few questions like, why didn't we use a single Elasticsearch index, a cluster, and why didn't you use the sharding in the Elasticsearch? So we can do that. Yes, but then what we want is actually for this feature, search nearby, we want a tighter control over our data and over the operational overhead, because the number of shards are fixed in an Elasticsearch, and in this case our data is increasing dynamically. So basically we want our routing algorithm, want to have a tighter control on our routing algorithm, and we want our routing algorithm to be flexible. So for this reason, we are handling the distribution ourselves using quadtree, and actually searching we are using the Elasticsearch for that. So this was all for this video. Thanks a lot for listening in. And basically this is one way of doing things. If you think there are multiple ways, or there are other ways which can be better than the way I have explained in this video, please feel free to jump in the comments and tell me about it. We can discuss, perhaps maybe make a new video. So have a good day.